Okay, welcome to this our continuing discussion on dimensionless groups, dimensional analysis and dimensionless groups. And I had discussed for you the fundamentals of dimensional analysis in the previous lecture. In any problem there is one dependent quantity which we want to calculate, and there is usually more than one independent quantities on which this dependent quantity depends. Okay. So, so in this particular problem that we had considered was of a particle settling in a fluid with a certain velocity v. The Newton's law for that particle basically says that the mass times the acceleration, okay, of the particle is equal to the sum of the forces exerted, and forces are the gravitational force, the buoyancy force, and this drag force due to the fluid. As the particle is settling through the fluid, there is a fluid flow around the particle, and this fluid flow causes friction, fluid friction, and a stress at the surface of this particle, which tends to decrease the velocity. And this drag force depends upon the fluid properties, okay, the velocity and the characteristic length of this particle. And we wanted to use dimensional analysis in order to simplify the expression for this drag force. Okay. So, that was the objective. I should note that the drag force does not depend upon the acceleration due to gravity, for example, okay, because gravity is a body force, whereas this drag force is due to fluid flow around the particle. Okay. It does not depend on buoyancy, for example. Okay. It depends only upon the velocity, because obviously if the particle does not move, the velocity is 0. It depends on the dimension. If it is spherical, it is the diameter, and the fluid properties. The fluid properties in this case are the velocity and the density. Okay. And so, we had gone through a dimensional analysis to find out the dimensionless dependent group and the dimensionless independent groups. Okay. There is one dependent group, and it can be non-dimensionalized by some independent parameters to get a dimensionless independent group. Similarly, in this problem we identified 5 independent dimensional parameters: the diameter, the length of the tank, the velocity, the density, and the viscosity. And on that basis, since they had 3 dimensions, mass, length, and time, we got 2 dimensionless parameters from the requirement that if there are n dimensional quantities and they contain m dimensionless they contain m fundamental dimensions, then there should be n minus m dimensionless groups. Okay. This is called Buckingham pi theorem. When there are n dimensional quantities and they contain a total of m fundamental dimensions, then there are n minus m dimensionless groups. Okay. The force we had initially scaled by the viscosity, okay, and we had got a dimensionless group which was the dimensionless drag force, okay, which is the ratio of the force, the viscosity, the velocity, and the diameter. Okay. And the independent dimensionless groups are the ratio of lengths, okay, and a second dimensionless group that contains the density, the viscosity, the velocity, and the diameter. That we had got by dimensional analysis, and that is what is called the Reynolds number, rho v d by mu. So, therefore, the relationship between these is in general of this form. Okay. The non-dimensional drag force F divided by mu v d is some function of the ratio of lengths and the Reynolds number. Okay. So, that is the relationship. This relationship can be further simplified in certain cases. If the length of the tank is much larger than the diameter of the particle, right, if the length of the tank is much larger than the particle diameter, then you would expect the flow locally around the particle to not be affected by the system size. That is because the distance from boundaries is much larger than the length scale over which flow takes place. The characteristic length scale for flow is about the particle diameter. Okay? So, if the distance to the boundaries is much larger than that, you would expect the velocity field to not be affected by the total size. And in an infinite medium, you can calculate the force without having to consider the total system size, and in that case it becomes only a function of Reynolds number. We have done a further reduction. Okay. When the Reynolds number is small, Reynolds number, as I said, is the ratio of inertial and viscous effects. Okay. The Reynolds number is the ratio of inertial and viscous effects. Density basically determines the inertia of an object. An object with higher density moving with a velocity has higher inertia, and viscosity in the denominator is is a measure of the viscous effects. So, when the Reynolds number is small, viscous effects are dominant. The density should no longer be a parameter, and we had got the result that the force divided by mu Vd has to be a constant. That constant we do not yet know. That has to be done by more detailed calculations of the velocity field around the object. But what we do know is that this ratio has to be a constant in the limit of low Reynolds number. In the limit of high Reynolds number, you can calculate the drag force by neglecting the dependence on the viscosity. Since viscous effects are negligible, therefore, the drag force can depend only upon the density, the velocity and the diameter, and we had got this inertial scaled drag force. I should note here that this relationship does hold for objects like sphere that are settling in a fluid, where the force, the drag, so if you have a sphere settling in a fluid, right, basically there is going to be a difference in the flow field between the upstream and the downstream side. Okay, as the sphere settles, the pressure on the upstream side is going to be different from the downstream side, because the fluid is incident on the fluid. The fluid is incident on the object on the upstream side, and then it goes around, and behind, typically at high Reynolds number, you have wakes and so on, which we will consider in a later lecture. Okay. And because of this pressure difference between the upstream and the downstream side, you have a force that is exerted on the object. Okay. And in this case, the drag coefficient, right, will depend only upon this pressure difference due to the lack of symmetry. Okay. On the other hand, if you have slender objects that are settling in a fluid, okay, whose cross-sectional area is very small compared to their length, then you do not have this difference, okay, but the drag force will depend on the shear stress, and viscosity is a parameter, okay, for slender objects. We will discuss that later, okay, when we discuss the flow past objects. For the present discussion, in high Reynolds number, you would expect that Fd by rho v square d square has to be a constant. The way the correlation is actually written for historical reasons is for the average pressure, that is the ratio of the force and the projected area. Okay. The area projected by the object in the direction perpendicular to the velocity field. Okay. That is basically an average pressure difference between the upstream and the downstream sides. Okay. That is scaled by inertial effects, that is the density, velocity and diameter. And if you do the dimensional analysis, you will find that this is the dimensionless group. Okay. In the denominator, I have half rho v square. Okay. Half rho v square is the kinetic energy per unit volume of the fluid, if the fluid were moving with velocity v. Half m v square is the kinetic energy of mass m. Divide that by the volume, you get a kinetic energy per unit volume. Okay. So, this is an energy per volume. Okay. And since energy is force into distance, energy per unit volume has the same dimension as force per unit area, which is the numerator. Okay. So, the dimension of energy per unit volume is the same as the dimension of force per unit area. Okay. So, if I take the force per unit area and divided by the energy per unit volume, I get a dimensionless group. So, that is how usually the drag force is defined. Okay. The drag coefficient is defined. Okay. For a sphere, okay, the projected area is pi d square by 4. Okay. For a sphere, okay, the coefficient is the projected area is pi d square by 4, okay, divided by half rho v square, okay, and this is equal to 8 f t by pi rho v square d square. Okay. If I just expand it out, okay, I will get 8 f t by pi rho v square d square, which is to within a multiplicative constant the same as the inertial drag force. Okay. Inertial, the drag force scaled by the inertial scales. Okay. So, this is how the drag coefficient is usually defined, okay, in these problems. Okay. So, I said that for in the limit of high Reynolds numbers, you would expect this drag coefficient to approach a constant value, because inertia is no longer a parameter in the problem. Okay. What about the at low Reynolds number? Okay. For Reynolds number, for low Reynolds number, f d is equal to f d is equal to 3 pi, I had said. This constant C 3 pi of course cannot be determined from dimensional analysis, but I am just using a result that I have not yet derived for you. Okay. So, this is drag force scale by viscous scale. Okay. The drag coefficient is equal to 8 f d by pi rho v square d square, okay, which will be 8 by pi, okay, into f d in this case is 3 pi mu v d by rho v square d square. Okay. Okay. I just substituted that the drag force is equal to 3 pi times this in the denominator, okay, in the limit of low Reynolds number. Okay. And you can easily see that this is equal to (24) into mu by rho v d, okay, which is 24 by the Reynolds number. Okay. Okay. So, if you scale the force by inertial scales in the limit of low Reynolds number, this force will be proportional to 1 over Reynolds number. Okay. So, the drag force when scaled by inertial scales in the limit of low Reynolds number will be proportional to 1 over Reynolds number. Okay. When you scale it by viscous scales, it will approach a constant value. Okay. We will come back to this discussion of the drag coefficient later, because we will see this in some detail as we go through the course. Okay. Let me go through some other problems, okay, using dimensional analysis. If I have an object that is rotating in a fluid, okay, with angular velocity omega, okay, and the object has diameter d, okay, a rotating object in a fluid with diameter d and angular velocity omega, what is going to be the torque that is exerted on this object? Okay. As the object rotates, it is going to start generating a velocity field, a rotational field in the fluid around it, and the fluid friction, okay, due to this rotational velocity field will cause a torque. Okay. So, what is going to be the torque on this object due to its rotational motion? Okay. in a fluid. So, the dependent dimensional parameter is the torque. Okay, we had already calculated what is the dimension of the torque. It is going to be equal to mass length square t power minus 2, if you recall. Torque has dimensions of force times distance. Okay. Force is mass into acceleration, ml t power minus 2. Multiply that by distance and you get ml square t power minus 2. Okay. What are the independent parameters on which this torque depends? Okay. Okay. Obviously, it depends upon the angular velocity. Omega, the diameter d, and the fluid properties. The fluid properties are density and viscosity. Okay. So, the angular velocity has dimensions of t inverse. We had seen that earlier. The angular velocity is basically the tangential velocity at a distance divided by the center, the distance from the center of rotation. Okay. The tangential velocity at a location divided by the distance from the center of rotation. So, it has dimensions of t inverse. The diameter has dimensions of length. Density is mass per unit volume, and the viscosity is mass length inverse t inverse. Okay. Therefore, I have 1 dependent and 4 independent dimensionless groups, dimensional quantities in this problem. There are 3 dimensions, mass, length and time. Therefore, I should be able to get 1 dependent dimensionless group and 1 independent dimensionless group. So, what is the dependent dimensionless group? It has to have torque, and torque has the mass dimension in it, and the mass dimension has to be scaled either by the mass dimension in the density or the mass dimension in the viscosity. There is subjectivity in how you choose which one to scale it by. In either case, in this case we will choose to scale it by the viscosity. Okay. So, I will write a scaled torque. Okay. I will use the symbol T, okay, for the torque, okay, is equal to T into the viscosity power A into the velocity power B, the length power C, okay, that is the diameter power C. Okay. Since this is a scaled torque, this has dimensions m power 0, L power 0, T power 0, okay, is equal to m L square T power minus 2, okay, into m L inverse T inverse power A, L T inverse power B, into L power C. Once again, equate the exponents of the fundamental dimensions on the left and the right sides. Okay. So, for mass dimension, 0 is equal to 1 plus A. Okay. For the length dimension, 0 equals 2 in the torque minus A, okay, plus B. Okay, there is a mistake here. It should not be the velocity, it should be the angular velocity, which is the independent quantity. Okay. Kindly note that it should be the angular velocity, which is the independent coordinate, and therefore, I should have this as T inverse power B times L power C. Okay. So, that is the relationship between the dimensions on the left and the right side. Equating the exponents of the fundamental dimensions, mass dimension 0 equals 1 plus A, okay, because I have mass dimension only in the viscosity and the torque. Okay. The length dimension, okay, 0 equals 2 minus A, okay, plus C, okay, 2 minus A plus C, and the time dimension 0 equals minus 2 minus A minus B. Okay. So, that is for the time dimension. Okay. So, once again you can solve these. This gives you that A equals minus 1. Okay. This will give us C equals minus 3, okay, because 2 minus A is plus 3. So, C is equal to minus 3, and this will give us B equals minus 1. Okay. So, therefore, the dimensionless torque is the ratio of the torque and mu omega d square d cubed. So, that is the dependent dimensionless group scaled by the viscous scales. And we know that there has to be one independent dimensionless group that involves these 4 quantities. Okay. I can go through dimensional analysis once again to get this independent dimensionless group, but I can get there quicker by realizing that in the previous problem the Reynolds number rho v d by mu was dimensionless, okay, and v has the same dimension as omega times d. Okay, the velocity is the angular velocity times the radius from the axis of rotation, okay, the distance from the axis of rotation, right. So, this dimensionless group I can write it quite easily as rho into something with the dimension of velocity into d by mu. Okay, because I know that rho v d by mu is dimensionless. Okay. So, this is rho omega d square by mu. This is the Reynolds number, in this case the ratio of inertial and viscous effects based upon the angular velocity of the object, of the rotating object, rather than the linear velocity. Okay. So, my dimensionless relationship is going to be that this is equal to some function of rho omega d square by the viscosity. Okay. And this functional form we do not know, we cannot find out just from dimensional analysis. We can, however, say that in the limit of low Reynolds number, when rho omega d square by mu is small, when inertial effects are small compared to viscous effects, then this torque has to approach a constant value when scaled by the viscous scale. Okay. So, for Re very much less than 1, T star is equal to a constant. Okay. We cannot evaluate this constant by dimensional analysis. You need to actually do the calculation. If you do evaluate it, you will find out that this constant has value of pi. Okay. In the limit of high Reynolds number, you would expect it to be scaled by the inertial scales. Okay. I will not proceed with that at this stage. Okay. You get a relationship that is very similar to what you get for the force on an object. Only thing is that you substitute omega times d wherever the velocity appears, and wherever the force appears, you take it as the torque divided by a length scale. Okay. So, that is the only difference. Okay. Let us look at another problem. Okay. Brownian diffusion of a colloidal particle. Okay. Colloidal particles are particles of size about 1 microns or less in a fluid. Okay. Dust particles, pollen grains and so on are colloidal particles, And if you actually look at the motion of a colloidal particle under a microscope in a fluid, you will find that it executes some kind of a random motion. Okay, it's called Brownian motion, and this is because it is being acted upon by the fluctuating velocities of the molecules in the fluid. The fluctuating forces of the molecules which are in thermal motion in the fluid exert a force, an instantaneous force, which is 0 on average, but because of instantaneous asymmetry between the forces exerted by molecules on one side of the object, okay, and the other side instantaneously, okay, you get this Brownian motion, this random motion of the particles. The displacement of the particle, okay, is usually, the displacement is usually written as the mean square of the displacement. Okay. If you take the average displacement, because it does not have preferential motion in any particular direction, the average displacement is always 0. Okay. But the square of the displacement is not 0, because when you take the square of the displacement, it is always positive, whether the displacement is in the plus x direction or minus x direction, the square of the displacement is always positive. Therefore, the square of the displacement adds up. Okay. And the square of the displacement is found to be proportional to the time interval of observation of this particle. Okay. So, if you actually measure the square of the displacement as it is undergoing Brownian motion, it is proportional to the time of observation. If you wait longer, it will spread over a longer distance. Okay. The square of that distance is proportional to time, and the proportionality constant is what is called the Brownian diffusion coefficient. Okay. The coefficient for Brownian diffusion. As in the case of mass diffusion, this Brownian diffusion coefficient also has dimensions of length square per time. Okay. This Brownian diffusion coefficient also has dimensions of length square per time, because it is equal to the square of the displacement divided by the time of observation. Okay. Now, this Brownian diffusion coefficient obviously depends upon the thermal energy of the molecules. Okay. If the fluid was colder at a lower temperature, the thermal energy is less, and therefore you will have less Brownian diffusion coefficient. When the temperature is higher, it will be more, and therefore you will have a higher Brownian diffusion coefficient. So, this is the dependent quantity, the Brownian diffusion coefficient. It depends upon it depends upon the thermal energy. Okay. And the thermal energy in turn depends upon the temperature, okay, and the Boltzmann constant. Okay. So, it depends upon the temperature and the Boltzmann constant. There is a thermal energy that is driving the Brownian motion of these molecules. Okay. Of course, as the molecule goes through the fluid, it is going to experience a drag force. Okay. At such small dimensions for colloidal particles, the inertial forces are not very large, but the viscous forces do exist. Okay. And therefore, the viscous forces resist the Brownian motion of this particle, and therefore, the Brownian diffusivity will depend upon the viscosity and the diameter, okay, of this particle. So, these are the independent quantities. There are 4 of them, and there is one dependent quantity, that is the Brownian diffusion coefficient. Okay. And let us see these independent quantities. What are the dimensions? Theta. The Boltzmann constant, energy per unit, the fluctuating energy is equal to kb times T. So, this has dimensions of energy per unit temperature. Okay. This was the dimension that we had got earlier. Viscosity is mass, length inverse, time inverse. And diameter has dimension of length. So, in this particular problem we have one dependent dimensional quantity, that is the Brownian diffusion coefficient, 4 independent dimensional quantities: the temperature, the Boltzmann constant, the viscosity and the diameter. They contain 4 dimensions: mass, length, time and temperature. Okay. So, therefore, total number of dimensional quantities is 5, dimensions is 4, there should be only one dimensionless group, okay, and that dimensionless group should be the scaled Brownian diffusion coefficient. Okay. Therefore, the dimensionless group that I will have, the scaled Brownian diffusion coefficient, has to be the Brownian diffusion coefficient, right. This is to the first power because that is the dependent dimensionless group. I will have the Boltzmann constant to the power A, the temperature to the power B, the viscosity to the power C and the diameter to the power E, okay, in this case. Okay. So, I can write the dimensions on both sides: m power 0, L power 0, T power 0, theta power 0, okay, is equal to the dimension of the Brownian diffusion coefficient L square T inverse, okay, into the Boltzmann constant m L square T power minus 2 theta inverse power A into theta power B into m L inverse T inverse viscosity power C times L power E. Okay. I use the symbol E here so as not to confuse with the diameter. Okay. Equate the dimensions on the left and the right sides. Okay. For mass dimension, 0 is equal to A plus C. Okay. Length dimension, 0 is equal to 2 from the Brownian diffusion plus 2A, okay, plus plus 2A minus C. Okay. Minus C plus E. Okay. Time dimension, okay, 0 equals minus 1 from the Brownian diffusion coefficient minus 2A, okay, and minus C, and the temperature, okay, 0 equals minus A plus B. Okay. And you can solve these equations. Okay. What you will find is that A equals minus 1, B equals minus 1, C equals plus 1 and E equals plus 1. Okay. Okay. You can see that A equals minus 1 and B equals minus 1 satisfies this equation. Okay. A equals minus 1 and C equals plus 1 satisfies this equation. Okay. And it also satisfies this equation: A equals minus 1 and C equals plus 1. Okay. Will satisfy this equation as well. Okay. And all 4 equations will be satisfied, which will give us the dimensionless Brownian diffusion coefficient as dB into mu into d by kb into t. Okay. So, that is what we get from dimensional analysis. Okay. Now, this, since there is only one dependent dimensionless group, that means that this has to be a constant. Okay. Which means that the Brownian diffusion coefficient has to be necessarily of the form constant into kb t by mu d. The Brownian diffusion coefficient has to be necessarily of the form constant into kb t by mu d. Okay. The value of the constant we do not know, okay, from dimensional analysis. Okay. Turns out that that constant is actually 1 over 3 pi, and therefore you get kBt by 3 pi mu d as the Brownian diffusion coefficient. Okay. And this is called the Einstein diffusivity. Okay. It was first calculated by Einstein in 1905. Okay. It is the ratio of the thermal energy divided by the drag coefficient in the Stokes drag law. You recall that in the limit of low Reynolds number, in the viscous limit I had said that the drag coefficient, drag force is given by the Stokes drag law, and this is the coefficient in the Stokes drag law. Okay. But up to this point we were able to determine using dimensional analysis. Okay. So, the torque on the particle and Brownian diffusion, simple examples of how dimensional analysis can be used. Okay. We will go on to a little more complex examples which are more relevant for transport processes in the next lecture. Okay. We will see you then.